Module 3, Lesson 5, The Power of Exponential Growth. So our instructional outcomes are going to be to discuss models with characteristics of an exponential function and to solve problems involving exponential formulas. In this lesson, we're going to look at an opening exercise and a couple of examples that model what this lesson is about. So for the opening exercise, it brings up this beginning discussion about two rental companies that rents out equipment for whatever purpose. And other two companies, one listed here in blue, one listed in green. Company one says on day one the penalty is $5. On day two the penalty is $10. On day three the penalty is $15. And on day four the penalty is $20, and so on. It increases by $5 every single day. So one thing that's interesting that we can note about that idea, that thought, is if we started with the penalty of $5 and wrote 10 and then 15, 20, and so on, the idea behind this lesson is for students to link what we talked about previously and note that each time that I am adding 5, so plus 5 each particular time, which our previous lessons had noted as an arithmetic sequence. Then it compares in the other company. It says company 2 on day 1 the penalty is 1 cent, so we could write down 0.01. On day 2 the penalty is 2 cents, and on day 3 it is 4 cents, and on day 4 the penalty is 8 cents, so on, that the amount each time is doubling what it was previously. So in that description we would say that this is a geometric sequence by what we talked about in previous lessons, whereas in each one we are taking and multiplying by 2 to create the next term. So the story goes on to say that Jim rented a Duggar from company 2 because he thought that it had a better late return policy. The job he was doing with the digger took longer than he had expected, but he wasn't concerned because the late penalty seemed reasonable to him. So when he returned the digger 15 days late, he was shocked by the penalty fee. And so the question goes on to say, what did he pay and what would he have paid if he had used company 1 instead? So this is an opportunity where the students get to sit down in small groups in class and kind of discuss and think about, given these two tables, as to what each one would look like. So we already kind of discussed what each sequence looks like. And so we know that if we went with company 1, it would be $5 for the first day. We had said $10 and then 15 and then 20. If we fast forwarded all the way through and looked all the way what the cost would be all the way to day 15, it would have cost Jim just $75 in a late fee. So we want to think about what it means to be arithmetic, and we said if we're doing an arithmetic sequence, then things tend to grow in a linear fashion or in a straight line. And so it's very constant. We can easily predict what it's going to be. Whereas if we look at the other company that Jim thought was reasonable, yes, the first day was 1 cent, and then 2 cents, 4 cents, and then 8 cents. That's what we stopped at on the previous slide. And so we noted that every single time we were multiplying by 2. So this one times this one, well, will be multiplied by 2 to get that one, and I would multiply by 2 to get that one, where opposed over here, I was simply adding 5 every single time. So if we fast forward this discussion as to what happens, there's 16 cents, 32 cents, $1.28 at 8 days. Still seems very reasonable. 9 days, $2.56 as compared to the $45 for 9 days there. But as we continue to go forward, $5.12, $10.24, $20.48. Still, we're looking at company 2 being a better price for a late fee of 12 days. Then all of a sudden we start to see a dramatic increase. We go from $20 from day 12 to about $40 on day 13. We double that And then all of a sudden we start to see a change or a shift. Company 1 all of a sudden at day 14 is cheaper than 14 days late on Company 2, and that's because we had to double our $40.96 to get $81, whereas in over here all we had to do was add $5 more to that. And so if we went to day 15, the penalty which Jim had to pay was $163.84. So when we look at that and we answer the particular questions, which company has a greater 15-day late charge, and we would want to mention that company number 2 is going to charge you more money. Question number 2 says, describe how the amount of the late charge changes from any given day to the next successive day in both companies 1 and 2. Well, we mentioned that. But in company 1, we're adding 5 every single day, and in company 2, we're doubling or multiplying by 2. And so they go on and ask, if that's the case, then what would be the late charge have been after 20 days for company number 2? Well, remember, company number 2 is geometric. And company number 1 is an arithmetic formula that works for each one. So if we looked at question number 3 and we want to write our geometric formula that we talked about in the previous lessons, our initial amount was 1 cent, which is what we started at. And every single day we are doubling or multiplying by 2. So then we raise that to the n minus 1 power. And so if we wanted to know exactly what our charge was going to be for that, we would plug 20 in for n. And then we would solve it. And once we plug that in and solve it, we would find that the late charge after $20 would be $5,242.88. And while it's not mentioned here, it might be worth asking the students, okay, well, if it is that high in company 2, what would the price have been in company number 1? And the students would say, well, we'll continue to add 5, or create that arithmetic sequence and calculate that for 20 and find out there is a dramatic difference in change. And again, the idea here is because our focus is on exponential functions and what they do. And so it's important students know that exponential functions grow real small at first. And that's why when we look at these values, they are growing at a relatively small rate. We're seeing 16 cents, 32 cents, 64 cents, when already over here we're up to $35. But the problem with exponentials is at some point, since we're doubling or growing exponentially, it will start to grow extremely quickly at some point. And we saw that point in which it grows extremely quickly start to really shift and change its dynamics when we get to this bottom end of the graph. From here on down, when we compare this part compared to this part, you start to see that grow. And so that's important to note that differentiation. And yeah, so depending on when you're going to turn it in late, company 2 is a great company to go with, but you need to be aware of how late you're going to turn it in and make your choice accordingly to make sure that is appropriate. In example number 1, studied by the students in class, it brings up this old folklore. The folklore suggests that when the creator of the game chess showed his invention to the country's ruler, the ruler was highly impressed. He was so impressed, he told the inventor to name a prize of his choice, anything he wanted. So the inventor, being rather clever, said he would take a grain of rice for the first square of the chessboard, 2 grains of rice for the second square, 4 for the third square, and 8 for the fourth square, and so on. And so we're seeing this idea of kind of what we talked about just now, of this doubling the number of what you had previously and the number of grains of rice for each successive square. The ruler was surprised, even a little offended at such a modest price, but he ordered his treasurer to go count the rice. So the question kind of starts off as a discussion for the class is why was the ruler surprised and what makes him think the inventor requested a modest price. And it really goes into the idea talking about the fact that exponential curves grow real slow at first. And so if you're thinking about the chessboard that he's playing on, he took 1 grain of rice for the first square, plus 2 grains of rice, plus 4 grains of rice, plus 8 grains of rice. And so when you think about that, the 1 plus the 2 is the 3, plus the 4 is the 7, plus the 8 is a modest amount, only 15 grains of rice. That's going through the fourth square. Now, it's important to note, some students may not know this, and this is illustrated on the next slide, is that there are 64 squares on a chessboard. And if we continue to double, then that 1 to 2 to 4 to 8, then to 16, and then the 32 is going to start to grow relatively quickly. And that's why the ruler was surprised. He did not stop and think about the later numbers being developed by this doubling, and just looked at the early on numbers and realized, well, that's a really small number as it continues to grow. So the example continues to look at saying that the treasurer took more than a week to count the rice in the ruler's store, only then to notify the ruler that it would take more rice than what was available in the entire kingdom. Shortly thereafter, as the story goes, the inventor became the new king of the kingdom, because it was the only way that the king could pay back the inventor for his price, because he did not have enough rice in his stores in order to develop it. So here we are, we're thinking about, we give this table to the students. Square 1 gave 1 grain of rice, square 2 gave 2, and 3 square gave 4 grains of rice, and so forth. And the students get to see the chessboard right here on the right as an opportunity to kind of see what's happening. And we note right here that we have 64 given squares on the chessboard. And so we go from our first square, to our 64th square, doubling every single time. And so we ask students to develop an exponential expression to represent each one individually. And so if we take a look at this and we wrote the expression 2 to the 0 power, that would be equal to 1 grain of rice. If we said 2 to the first power, then that would be equal to 2 grains of rice. If we said 2 squared, that would be equal to 4 grains of rice. And so the student starts to see the connection with this column here and the expression that's being used each time to develop it. So here we are with our 2 to the 0th power, 2 to the 1st, 2nd, 3rd, 4th. And so the students are asked in part C to write the expressions for the squares of 62, 63, and then 64. So looking at the pattern and the experience discussed through the discussion, the students would come up with 2 to the 61st power, 2 to the 62nd power, and then 2 to the 64th power. And again, the reason why that works, if we look at that geometrically, and we look at our geometric formula, we mentioned that ace of n, or the term that we're talking about, is equal to the first term, the a term, times the common ratio, or basically what we're multiplying by every single time, raised to the n minus 1 power. So as the story goes, we started off with 1 grain of rice. So that's our initial piece, that's our 1. It also helps the student to understand or explain where this 1 came from and why 2 to the 0 power is equal to 1. So we're doubling by 2 every single time. And then we have our n minus our 1, or the square number that we're on. So 1 minus 1 would be 0, 2 to the 0 power. And all we're left over is this 1. And so forth. And so sometimes we may challenge the student, put 2 to the 64 power in the calculator and find out what it gets. And so I won't do that here. But a lot of students are really amazed when they plug that into their calculator and see what happens and what they get given that situation. In example number 2, we look at this difference between arithmetic and geometric a little bit closer by comparing the two ideas or notions of f of n equals 2n, which is our arithmetic, versus our 2 to the n power, which is our geometric or exponential. So we ask the students to complete the tables below and then graph the points for each one on the coordinate plane so we could compare. So we ask the students, well, all right, if we plug negative 2 in for 2n, so we plug 2 in, negative 2 right here, so 2 times negative 2, and that's going to equal negative 4. And then so 2 times negative 1 will equal our negative 2, and we'll continue on down the line getting these following results: a 0, a 2, a 4, and then a 6. So of course we are asking the students to graph this on the graph so they can see what's going to happen. So if we take negative 2 and then negative 4, we plot that, that'll be right here on the graph. Negative 1, and actually this negative 2 times negative 1 is actually negative 2. So we end up with negative 2 down here, negative 1, negative 2, 0, 0, 1 comma 2, 2 comma 4, and then 3 comma 6. And so we see this linear pattern, or this line, starting to develop when we go through. And so I'll just draw a line through that to kind of show that movement, that this is what an arithmetic sequence is going to look like. That's what it's going to do. When we take a look at this one and we raise 2 to the negative 2 power, 2 to the negative 2, and depending on how you want to write it in your class, depending on your teacher, this will either be known as 1/4, or your teacher may permit you to write it as a decimal as 0.25. Again, check with your teacher as to how they want it to be written. Again, if we continue on, this would be 0.5, this one would be 1, 2, 4, and then 8. So if we plotted those points on the graph at negative 2, 0.25, well, that's down here real small. It's a very small value. And then negative 1, 1/2 is right here. 0, 1, 1, 2 matches right there, and then 2, 4, but then you notice 3 goes up to 8. So when we compare the curves, and I'll draw it out as best as I can draw the curve out, you get this idea where it starts off real slow at the bottom, and it starts to grow as we move up, and it starts to curve off this way. So you start to see that exponential curve grow real quickly, which is again harking back to what Jim misinterpreted, and the same thing as the ruler misinterpreted when they thought the number started off real small. That was a real modest price or fee or what was reasonable. You just have to know your limits and know when it starts to double compared to an arithmetic and a geometric, because they're both important and both work properly for given situations on what you want to do. So the last thing we're going to look at is a follow-up exercise. Brings back something we talked about in a previous lesson. So we'll start with that, saying to recall the future value, which is right here, equals the principal value times 1 plus the rate raised to the time represented by t. So if we look at the word problem in exercise number 2, it says a rare coin appreciates at a rate of 5.2%, or which is also known as 0.052 as a decimal. The initial value of the coin is $500. How many years will the value will it take for its value to cross the 3,000 mark? Show the formula that will model the value of the coin after t number of years. And so we want to know when it will be worth $3,000. So that's that future value that we're looking at, 3,000. We started off with the principal value being $500, and we're going to have that being raised to the 1.052 raised to the t power. And so we'll, when you solve that and go through that, and we won't go through that info because we just want to talk about, highlight this particular formula here. But for those that want to know the time frame in which that's going to work, and we challenge the students individually to come up with their own idea of how they want that to work. And so that ends up being t equals 35 years. So I challenge you to take a look at that. If you have a difficult time getting that, by all means go see, contact your child's teacher to get more specifics on how to attain that t, but that's not what part of this discussion is for me in this lesson.